Hello and welcome back to Math 301, Introduction to Combinatorics at CSU. Today we're going to be talking about the basics of set theory to put some of the combinatorial principles that we've been learning, the addition principle, the subtraction principle, the multiplication principle, on a more rigorous foundation. So what is a set? A set is an unordered collection of distinct objects. You want to think intuitively of just a handful of things or a bag of things. There's no particular order, and things can't appear more than once with multiplicity. So as an example, the set containing 2, 3, 5, 8, A, and star is a perfectly good set. You can have numbers, you can have symbols, you can have people, you can have anything you want in a set. And you write it with squiggly brackets like this. That denotes that it's a set, whereas something like parentheses might indicate that there's an order specified to it. But there's no order. In particular, if you write 2, 3, 5, 8, A, and star, that's the same set as writing the set containing 5, 2, A, 3, star, and 8. There's no particular order, it's just the data of which things are in the set. Those things that are in the set are called elements, and the elements of this set are 2, 3, 5, 8, A, and star. Notice all the elements are distinct, so we don't have, say, 1, 1, 1, 3, and 4. That's not a set, it contains 1 too many times. We will talk in the future about multi-sets, which do allow multiplicity in our sets. But for now, we're only going to do sets containing each element exactly once, like 1, 3, and 4. Let's talk about different ways of writing down a set. So my favorite way to write down a set is a blob diagram. You draw a circle or an oval or whatever shape makes sense as your blob, and then you put the elements inside with little dots. And so sometimes elements of sets are called points of the sets. And I'll sometimes say 2 is a point of this set here. Here I can also write it in set notation. 2, 3, 5, 8, A, and star. You can set that whole set to be a letter like S. And then the symbol, this little E, means element of. So 2 is an element of S, because 2 is in this set, and star is an element of S, but 1 is not an element of S. I don't have any point labeled 1 in this blob diagram, and there's no 1 in this set notation either. Now the cardinality of a set is the number of elements. This is something we're going to be working with a lot. How many elements does a set have? Combinatorics is all about counting. And here we have 1, 2, 3, 4, 5, 6 elements, and so we write the cardinality of S is 6. This absolute value sign around a set means the number of elements in it, or the cardinality. Let's talk about some famous sets. One is the natural numbers. This will come up a lot in combinatorics because everything we count is going to be a natural number. A natural number is just a non-negative integer. So starting at 0, it's the counting numbers. 0, 1, 2, 3, 4, ... So we write n to denote this set, boldface n, and this n is an infinite set. We saw a finite set in a blob diagram before, and infinite sets are harder to write down, so you'll need ... or some description of the set. The integers are another famous set, and these just include the negative numbers as well as the positive numbers, and you use z to denote the integers, for the German word for number. The rational numbers you denoted q. This is the set of all fractions, a over b, where a and b are both integers. And if you put the irrational numbers in, as well as the rational numbers, you get the real numbers, which includes irrational numbers like pi and square root of 2, and it also has all the rational numbers and the negative integers and the negative rational numbers and everything. The real numbers is the whole real line. Finally, there's one more famous set that I want to talk about, and it's much, much smaller than any of these four. It's the empty set. The empty set is the set with nothing in it, and it's a perfectly well-defined set. We even have a special symbol for it, a circle with a line through it, and we also can write it as squiggly brackets with nothing in between them. Now that we have big sets, we can define subsets of them. A subset of a set is just a collection that's sort of a sub-collection of the big collection. Formally, a set A is a subset of a set B, which we write A as a subset of B. That's the subset symbol. If every element of A is also an element of B. So everything in this circle is also in the big circle, so the little circle is a subset of the big circle. In set notation, we would write 3, 5, and star for this subset is a subset of the big set, 2, 3, 5, 8, A, and star. Now subsets are different from sets that are elements. Sets can actually contain other sets as elements because a set is just a collection of things. Those things can be sets themselves. So you can make nested sets if you'd like as well. And this will come in handy when we do set partitions and the division principle. In this example, I've written down a set containing 2, containing the set containing 3, 5, and star. It contains 8, and it contains A. And now, instead of the set 3, 5, and star being a subset of this big set, it's now an element of this set S that I have in the blob diagram. And so I draw it with a point instead of with a circle around 3, 5, and star. In fact, the cardinality of this set is 4. it's not 6 because I've merged these 3 elements into one set and consider it one element of the big set. Now that we have subset notation and understand elements, we can make new sets out of famous sets or out of other sets that we already have. And the most powerful tool to do that is set builder notation. You write the set bracket of x in some set A. So this is read, you read it like the set of all x in A. And then this line means such that x has property P. So you'll have the set of all x in A, again the midline means such that, and then there's some property that you want x to satisfy, and you only take those elements of A and you put them all in that set. So here's an example of how you use set builder notation. If I write the set of all x in the natural numbers such that x is less than 5, well that's all the natural numbers less than 5, which is 0, 1, 2, 3, and 4. There's nothing else. And so we've built a set using set builder notation. I start with all the natural numbers, and I restrict it to having the property that x is less than 5. Here's another example of a subset of the natural numbers. The set of all n in the natural numbers. Notice it doesn't matter what variable I use. I could use x, I could use n, as long as the property is about that variable. And in this case, my property is that n is even. So now I'm just listing the even natural numbers, 0, 2, 4, 6, ... This one is an infinite set, this one is a finite set. Sometimes the property makes a very small subset, sometimes it's a very large subset, sometimes it's the whole thing, sometimes it's the empty set. Set builder notation lets you make a lot of new sets out of old sets. Here's a slightly different way to do set builder notation. Sometimes you actually put the set you're starting with on the right, and you actually put the output on the left of some function. So if you have some function f of x, then you could write down the set of all f of x such that x is in A. And what that means is, for instance, if we do the set of all 2 times k, such that k is a natural number, it returns 2 times every natural number and sticks it in a set. And so this is another way of writing down the even numbers. If you didn't want to write the phrase n is even, you can actually just say the set of all 2k, such that k is a natural number. So now that we've established the basic notation for sets, let's talk about some set operations. One is the operation of union, which takes 2 sets that we're going to draw as a Venn diagram here. This circle is the set A, and this circle is the set B. And the union, denoted A union B, this little u is called union, is the set of all x such that x is either in A or in B. Now, the element 2 here is in A or B because it's in A. Also, the things that are in both are considered to be in A or B. It's not exclusive or. And the elements over here are also in A or B because they're in B. And so the union is basically if you draw the Venn diagram and shade everything in the way I've colored it here, then you get all the elements together. So even if they have some overlap, you just count them once on the right, because remember, sets don't have any element occurring more than once. So the union of the set 2, 3, 5x, this set A on the left, with 3, 5, 8, x, and star is 2, 3, 5, 8, x, and star. So we've just listed each of these elements exactly once in the union output. So that's union, and another very important operation is called intersection. So the intersection of 2 sets, written A intersect B, and the intersection symbol is just you take the U symbol for union and you turn it upside down. So A intersect B is the set of all x such that x is in A and x is in B. And the and means that they have to be in this overlap between the 2 circles. So I've shaded the region that the intersection corresponds to here. And so the set 2, 3, 5x intersect with the set 3, 5, 8, x, and star is just the set 3, 5, and x. Just these 3 points that are in the middle between the 2 sets. Now, how do these relate to the addition principle and subtraction principle? Well, union is almost like plus, because if you have a collection of A things and a collection of B things and you put them together, you have A plus B things, unless they have overlap. So the way we can express the addition principle in terms of set theory is in terms of what's called disjoint unions. 2 sets A and B are disjoint if A intersect B is the empty set, meaning there's no overlap between these 2 sets, and you don't have to draw the Venn diagram overlapping then, you can just draw them as 2 separate circles. If they're 2 separate circles, if they have no element in common, then the addition principle says if A and B are disjoint, then A union B, the size of it, is the size of A plus the size of B. In this case, we have a set of size 4 and a set of size 2, and we take their union, and we get a set of size 6. Just all of them together in one bucket. Now, how do we do minus? Well, set difference is another operation on sets. The set A minus B is the set of all x in A such that x is not in B. In Venn diagram notation, if this is set A and set B, it would be this little wedge over here, where it's all the points that are in A, but not in the circle B at all. Now, this doesn't exactly correspond to subtraction unless you're dealing with subsets. So let's go back to our subset picture. And if B is a subset of A, then the size of A minus B is the size of A minus the size of B. That's the subtraction principle. What that's saying is if you get rid of the subset here and just look at the stuff outside, then you take the whole number of points and you subtract the ones in the little circle and you get what's left over. Now, what about the multiplication principle? We need one more operation on sets, and that's called Cartesian product. A cross B is defined to be the set of all pairs A comma B, such that A is in A in big A and little b is in big B. So we're taking the set of all pairs where we take one element from the first set and one element of the second set. Let's do an example where we take the set XYZW cross the set 1, 2, 3. Well, we have all the pairs x with everything, x comma 1, x comma 2, x comma 3, and then all the pairs with y with 1, 2, and 3, and z with 1, 2, and 3, and w with 1, 2, and 3. And you notice I've organized these in a little 3x4 table. The multiplication principle then says that, yes, it's 3x4, so there's 12 elements. So the size of A cross B is always the size of A times the size of B. And you don't need any special subset condition or disjoint condition. This is always true for Cartesian products. In some sense, a Cartesian product is saying, pick one thing from A and pick one thing from B. And so that's where that and then is coming in when we translate to set theory. Finally, let's do a combinatorics problem with sets. In particular, I want to count all the subsets of a 5-element set. How many subsets are there? We can start listing them. There's the empty set, there's the set containing 1 and 3, there's the set containing 2, 4, and 5, there's just the set containing 4, that's a subset. You can take the whole thing as a subset, 1, 2, 3, 4, and 5. You can actually phrase this problem as an and then problem and use the multiplication principle. Because if you think about it, a subset is defined by which elements from the big set are in that little set. We just have to choose for each of the 5 elements whether they're in our subset or not in order to make a subset. So there's 2 choices for whether 1 is in the subset or not, 2 choices for whether 2 is in the subset or not, 2 choices for whether 3 is in the subset or not, 2 choices for whether 4 is in the subset or not, and 2 choices for whether 5 is in the subset or not. And we've made those choices sequentially and independently, and so we multiply them all together. 2 times 2 times 2 times 2 times 2, which is 2 to the 5th, or 32 subsets of a 5-element set. And yes, in general, if there's an n-element set, there are 2 to the n subsets of it. So now you try, how many subsets of the set 1, 2, 3, 4, 5 do not contain 4? And that's all for today, and I'll see you next time.